in this episode.
Engine is running, yes, engine is running.
Já começa aqui, ó.
The biggest oil tanker on the planet.
This is a massive ship.
There is no any other vessel that can be compared with this one.
And the groundbreaking innovations from history.
It's an amazing piece of engineering. It was something that really hadn't been done before.
That make the impossible possible. Oceans cover 70% of the Earth's surface. They're our planet's life support system and a lifeline for global commerce. The seas are the highways for world trade, and it's estimated that thousands of boats and ships are operating on them at any given time. Naval architect Nick Bradbeer is at a simulator at Solent University, Southampton, that allows him to recreate today's heavily congested shipping lanes.
Global trade has driven a huge increase in the amount of shipping in the world. 90% of goods moved around the world move by sea, and most of them move across a relatively small number of important shipping routes. Some of those routes pass through quite narrow choke points, and those areas might see 600 ships passing in a single day. They get very busy.
The modern cargo ships that fill these shipping lanes are sophisticated machines. But it's taken engineers years of pioneering innovation to get here. Around 1200 AD, the first ocean-crossing traders were the Polynesians, crossing from island to island in canoes. By the 1500s, Sir Walter Raleigh and Sir Francis Drake used galleon ships to sail around the globe exchanging goods. But it wasn't until 400 years later that Norwegian Roald Amundsen crossed the final frontier, the Arctic waters of the Northwest Passage. Today, thousands of ships travel these same routes, creating a massive traffic jam. With more and more goods to move along these busy maritime highways, many experts believe the solution isn't to build more ships, but to build bigger. This is Supertanker Europe, the biggest oil tanker in the world. It's capable of carrying almost half a megaton of cargo through some of the harshest seas on the planet.
It's an incredible machine. This is just an absolutely enormous ship.
The nerve center of this colossal machine lies 6 floors above deck on the bridge. From here, Captain Nedeljko Labrovic navigates the crude oil on board around the world.
Crude oil is the world's biggest commodity, and it represents nearly 1/3 of the global maritime trade. And worldwide demand for the crude is constantly growing.
With so much cargo to transport, engineers had to build a ship on an unprecedented scale.
It really makes me proud to be captain of such an amazing vessel, one of the biggest ships in the world at the moment.
Supertanker Europe is 249 feet high with a 1,247-foot long deck. It's capable of holding 7 times its own weight in crude oil, enough to fill 15,000 road tankers. The monster ship is pushed through the water by a 103-ton propeller and steered by a rudder that weighs an incredible 251 tons.
All parts of this vessel, comparing to others, is much stronger and much bigger.
Okay, we're running engine.
Okay.
Everything about this vessel is supersized, even the anchor chains that are stored in lockers at the bow of the ship. Their job is to pull up the anchors that weigh 24 tons each. It may seem like a simple task, But on a supertanker, this requires some epic engineering.
Anchor chain leading going to 1 o'clock.
Please proceed, let me know when you start.
Okay. We are commencing here.
These anchors need to be strong enough to hold the fully laden 551,000-ton ship in place. Their chains alone weigh 340 tons.
I'm here to monitor the tension of the chain. All these informations I'm giving to the captain, who is controlling the main engine. Now it's 12 o'clock, moderate.
Engine is running, yes, the engine is running.
Okay, copy. Still running.
It takes an elite crew on board to operate this incredible machine.
Anchor at home.
Anchor at home, okay.
You are aware that you are part of a team that can handle this size of vessel. Stop. I was dreaming to work on it, and now I have opportunity to be part of this team.
And this ambitious supertanker needs a team of engineers that aren't afraid to push the boundaries.
To design, build and run a ship of this size requires us to overcome some seemingly impossible engineering challenges. The first thing is, how do you build a ship this long, strong enough that it won't just snap in two at sea? How do you prevent millions of litres of flammable cargo from catching fire or exploding? And finally, how do you build an engine powerful enough to push a ship this big through the water?
Designing, building, and operating a ship of this size is a seemingly impossible engineering challenge.
Now, the real challenge in designing a ship structure is the middle. When a ship moves through waves, they bend it up and down. And we need to make sure the structure is strong enough that the ship won't break its back, especially in the middle. That's where those bending loads are the greatest, and that's where it's most likely to break. Now, as a ship gets longer, those bending loads get bigger and harder to design to resist. For a ship as big as this one, building a structure that's strong enough is a real challenge.
Supertanker Europe is wide enough and long enough to carry over 2,000 cars on its deck. So gigantic that unassisted, it takes over 3 miles and up to 21 minutes to come to a stop. For a ship this massive, with such slow braking ability, any type of impact could be devastating. And out at sea, danger can come in many shapes and forms.
When you are in bad weather, each seaman will have questions: is this vessel capable to pass these seas on safe way?
This is Supertanker Europe, the biggest oil tanker in the world. Capable of carrying over 100 million gallons of crude oil on board. Everything about this ship is a feat of supersized engineering. It's as tall as a 24-story building and 223 feet wide, double the size of the locks on the Panama Canal. At 1,247 feet long, it's much larger than the Titanic. But out on the open ocean, gale force winds can hit 43 miles per hour, with waves over 33 feet high. This is a brutal environment, even for a supertanker. For Chief Officer Josip Ivanov, one of the biggest threats is the unpredictable force of nature.
Even one impact can bring big problems to the nature and to the sea. You must be sure that your vessel is built good to pass all these heavy seas. For engineers, for sure, it's a big challenge to make it strong enough and safe enough.
To make sure this massive ship stays unbreakable, even in the roughest waters, engineers looked to a pioneering innovation of the past. Naval architect Nick Posh is at the Menominee River in Michigan, home to one of the earliest examples of a revolutionary design.
Wow, there it is. This ship, the William H. Donner, was built in 1914 and was in service for about 100 years.
The William H. Donner is huge, once carrying up to 22,000 tons. And this ship once worked in one of the toughest trading environments in the world. Trading iron and coal across the Great Lakes has been testing engineers for centuries.
The demand for ore and coal at the beginning of the 20th century grew very rapidly, so ships had to grow bigger in order to carry more cargo. But some weren't strong enough for the task. Some were literally breaking their backs.
In 1906, British naval architect Sir Joseph Isherwood created an ingenious way to build massive, strong ships. Known as the Isherwood system, his invention was a unique internal framework running from bow to stern and leaving no weak spot in the middle.
This is an awesome piece of marine history. You don't see very many intact ships this age anymore.
Nick is making his way to the deepest part of this historic wreck to find out how the William H. Donner has survived for so long.
Wow, you can really tell this is a really old ship with all the rivets you have going on right here. This is a very old method of shipbuilding. Watch your step. So this looks like to be the old coal room. Oh, geez. Don't step on that. This is where they would basically feed the boilers to propel the steam turbine to propel the ship. Oh, what's in here? Oh, there is an old anchor chain in here, and actually an anchor. So it really feels like you stumbled into a treasure trove in here because of all the history. I feel like an ant in here is what I feel like, so.
But the ingenious idea that paved the way for bigger, safer ships lies even further below.
Wow, this is a really tiny hole. Through this hole, it looks like you'll be able to get all the way to the bottom of the ship. I'm not sure if I'll be able to fit in here, but we'll give it a go. Let's see if I can fit here. So far, so good. And here we go. Oh, I'm caught. Here we go. All right.
Here, Nick can finally see the secret to how this ship has lasted for over a century.
So these big transverse frames form a giant belt around the hull. They serve a structural purpose in that it keeps the ship from collapsing in on itself. The longitudinal frames you see here keep the ship from bending long ways or longitudinally.
Traditional ships were constructed with closely spaced transverse frames from the keel up to the deck. But over time, as ships got bigger and cargo got heavier, this structure couldn't keep up. But by using a combination of transverse frames with more tightly spaced longitudinal frames, the Isherwood system was born, and with it, the ultimate strengthening solution.
It feels pretty cool being down here and seeing the way they constructed these massive beasts. Without the modern aid of computer design, teams had to lay all these giant pieces out in a large template to build these sorts of ships. And they had to calculate everything by hand, and one miscalculation could literally break the ship's back.
Nick has made it to the cargo hold of the vessel, where he can check out the innovative system in action.
It's so massive because the Isherwood system allows the vessel to be a lot lighter because of less structure, and allows to carry more cargo, which is the reason for this huge cargo hold. And on the side here, you can also see the indents of where the longitudinals are, as well as the transverse frames, widely spaced.
Isherwood's ambitious design paved the way for the mighty cargo ships of the future.
The majority of the tankers are built using the Isherwood system today, including the TI-class supertankers. I really admire Isherwood for coming up with this concept because it is such an innovative design and really changed the course of shipbuilding throughout the years.
The massive supertanker Europe uses the Isherwood system on an unprecedented scale. Chief Officer Josip Ivanov is heading to where the brute force of the ocean hits first, the bow. Hidden below are over 10,000 transverse and longitudinal frames built on a monumental scale. A testament to one man's incredible engineering vision that made it all possible.
It's exciting to be here on this place because this is the first place of the impact on the vessel. Everything it's built to be massive, to be strong and made of good materials, to have a life of the vessel for 40 years. All this structure is made on the Isherwood system.
The supertanker remains one of the most impenetrable tankers on the ocean today. It has two hulls, one sitting inside the other for double the strength, making this the biggest double-hulled ship in the world. Supertanker Europe, the largest double-hulled vessel in the world. Inside, 21 separate cargo tanks are loaded with over 100 million gallons of crude oil. But this cargo is highly flammable and could destroy the ship in seconds.
The danger starts as soon as we start to load it onto the ship, through a system of pipes like these, and then across to the cargo holds and down. As we have millions of litres of thick oil being forced at high pressure through these pipes, we get friction, and that leads to a buildup of electrostatic charge, which can cause sparks. Once the cargo reaches the cargo holds, it's sitting in these enormous tanks, mostly full of flammable oil, but also full of evolved flammable vapours. This is potentially a floating bomb, and so it's critically important that we make it as safe as possible.
Deep below deck lies the heart of the oil distribution system, and the most dangerous place on the ship, the pump room.
Pump room is definitely one of the critical places on the vessel. This can happen in case of some leak of cargo that we carry. There is a potential of explosive and toxic gases. All equipment that we are using in the pump room should be explosion-proof.
Many ships have a pump room, but few are built on this scale. Supertanker Europe's pump room houses not one, but 3 massive pumps capable of discharging up to 276 tons of crude oil per minute. The oil is brought on board and discharged to the cargo tanks before being offloaded at its final destination. But one of the dangers that can strike at any time during this process is a rise in temperature. When oil heats up, it vaporizes. The hydrocarbon gas that is created can cause a critical rise in pressure, enough to blow a massive hole in the ship. The elite team that operates Supertanker Europe protects the oil cargo by deflecting the burning rays of the sun. 270,000 square feet of surface area are constantly maintained with fresh layers of white reflective paint. Pumpman Ferdinand Guevara manages any pressure fluctuations from the deck.
This is the pressure vacuum valve. This is to control or maintain the pressure inside the tank.
But the pressure caused by the gas and vapors isn't the only issue.
The atmosphere in this tank is very flammable. One spark, it will explode. So we need one system to keep everything safe.
To eliminate the threat of an explosion, engineers must look to the innovators of the past. Engineer Luke Bisbee is at the Royal Air Force Museum in the UK to uncover an engineering secret hidden inside one of the most iconic aircraft ever designed for service during World War II. The Avro Lincoln.
I can't believe how little space there is in here. It's really tight, really claustrophobic.
First taking to the skies in 1944, the Lincoln's long range made it perfect for bombing raids over Germany and beyond. But the plane and crew were also at risk of being hit by anti-aircraft fire from the ground.
Bomber planes were built by both sides for some of the war's most dangerous and deadly missions. The bomb aimer would sit down here, just below the cockpit, charged with aiming and releasing thousands of pounds of bombs. And these were truly devastating machines, so both sides did all they could to stop them reaching their targets. If an engine caught fire, most planes of this era had sensors and switches which triggered fire extinguisher systems. And these systems were quite effective at fighting engine fires, but protecting the huge fuel tanks was a much bigger challenge.
The Lincoln's engineers had to find a way to ensure that if the plane was hit, its fuel tanks wouldn't explode.
Liquid fuel is surprisingly stable, so a full tank, if struck, is unlikely to catch fire. The problem starts as the fuel is used up. Any flammable vapor left in the tank is highly volatile, so a part-empty tank struck above the fuel line will explode.
Planes flying across Europe would have partially drained their fuel tanks by the time they encountered anti-aircraft fire, limiting their chance of survival. But in 1943, aircraft designer Roy Chadwick incorporated an ingenious discovery that changed the future of aviation and could help solve a potentially explosive problem on supertanker Europe.
This system was based on a very simple principle. Fire needs oxygen. So if the oxygen's reduced, there's less chance of a fire. So what I'm going to do is put some fuel into this receptacle. And we can imagine this being the fuel tank of a bomber, for instance. And then if I take this fuel and I just shake it around, and in doing so, I generate flammable vapor inside my fuel tank. Whoa, I certainly would not want to be on an aircraft with that going on out on the wings.
Next, using an identical fuel-filled bottle, Luke's able to show an engineering breakthrough that reduced the level of oxygen.
So this time, I'm also going to add to my bottle an inert gas, and in this case, I'm going to use nitrogen. And so now you can see I've got my fuel tank, and inside it I have my flammable vapor as well as now nitrogen. And let's see what happens when I hold a match. And you can see here now the nitrogen is doing its job, and I'm not getting any combustion whatsoever. And I can even drop the match into this tank. So here we are, safe and sound with our inert gas system, and I'm much, much happier on this bomber. And that's because nitrogen, along with other gases like carbon dioxide, is inert, thus displacing oxygen and preventing the violent combustion. And this was the key to protecting the planes.
In 1944, the first inert gas system was installed in the Avro Lincoln.
So I'm now in the central portion of the aircraft, and the wings are extending either side, on that side and on that side. And at this location, there would have been a series of nitrogen tanks, much like these oxygen tanks, and they would have been plumbed into the fuel system. The nitrogen was fed at high pressure through brass tubes to filters and valves, out along the wings and to the vent pipes feeding the 6 fuel tanks. And as the fuel was depleted, the tanks were steadily filled with nitrogen to ensure that the fuel vapor couldn't combust. and the inert gas system became a life-saving solution for many industries, from the skies to the seas.
To create supertanker Europe, engineers took the inert gas system and combined it with some even more impressive engineering solutions. Since 1944, the inert gas system has prevented explosions on countless aircraft and ships throughout the world. But the engineers behind supertanker Europe have taken it one step further. This supertanker doesn't just use inert gas. It carries all the machinery and equipment on board to manufacture and distribute it. It keeps oxygen levels in the oil tanks as low as 5%. Chief Engineer Zlatan Hirov is heading to the ship's stern, where the inert gas system is housed. This entirely self-sufficient inert gas system spans 3 floors. At the bottom is a 33-foot-tall heating system.
This is our oil-fired boiler. The exhaust of the boiler we use to create inert gas.
The boiler generates the inert gas, which is siphoned off to the floor above.
The exhaust gases from the oil-fired boiler are cleaned and cooled in the scooter towers.
Inside each tower, a shower of seawater cleans and cools the gas. Next, it travels to 3 massive centrifugal fans on the top floor that propel it to the cargo tanks, where it sits above the volatile oil, preventing a buildup of explosive vapor.
Building a vessel like this is a real progress of the present marine engineering.
The inert gas system is one of the most important integrated systems ever designed for an oil tanker, making a volatile liquid stable and safe enough to load and transport across oceans. But before supertanker Europe can actually transport anything, engineers face another major challenge when it comes to moving this massive ship through the water.
One of the huge challenges in building a supersized ship like this is providing enough engine power to move it through the water, including through some of the world's worst weather conditions.
This giant vessel is heavier than 100,000 elephants and soars 249 feet high from below the ocean to the top of the bridge. On board, a total of 13 floors house the machinery and equipment needed to operate this impressive but complex ship. This colossal creation must be able to hit speeds of 19 miles per hour, even in the harshest environments. Nick Bradbeer is in the simulator at Solent University, recreating the conditions often faced at sea.
One of the huge challenges in building a supersized ship like this is providing enough engine power to move it through the water, including through some of the world's worst weather conditions.
In the Atlantic Ocean, the average wave is 11 feet high, but monstrous waves reaching 95 feet high have also been recorded.
Now, to push a ship through that kind of weather, we need a lot of engine power. The engine needs to be very reliable. We can't afford for it to break down. And when we're burning as much fuel as we are on a ship this big, we really need a very efficient engine as well. So we want power, reliability, and fuel efficiency. Any one of these 3 is a significant challenge, but to have all 3 together in the same engine, now that's tough.
Engineers need to build the perfect engine that will be capable of moving over 550,000 tons of ship and cargo. But first, they'll have to take an up-close look at one of the most powerful breakthroughs in history.
These are trains that haven't been seen on the railways in decades.
As it powers across the Atlantic Ocean, supertanker Europe will be exposed to the often unpredictable elements, and this mega vessel will need an engine strong enough to push all 550,000 tons of it through any situation it encounters. The solution can be found in an important but nearly forgotten piece of history. Engineer Agnes D'Entremont is visiting a remote train yard in Alberta, Canada, where North America's post-World War II economy saw an increase in demand for bulk goods.
This is so cool. These are trains that haven't been seen on the railways in decades. Steam engines, which were the freight haulers of the time, were just not reliable enough, and they required a lot of maintenance and upkeep. And so a new solution was needed for this new freight demand.
The solution can be found in the General Motors F3 diesel locomotive.
Wow, that thing's big.
This is the engine that transformed North America's railways and could hold the key to powering the mighty supertanker Europe.
This is an EMD 567 two-stroke diesel engine.
In 1899, German engineer Hugo Guldner designed the world's first two-stroke diesel engine. And in the 1930s, General Motors perfected the concept, creating one of the most successful diesel engines of the mid-20th century.
So this is a 16-cylinder two-stroke diesel engine. There's 8 cylinders on this side, 8 on the other side in a V pattern. Behind each one of these valves is where the cylinder sits.
A typical diesel engine takes 4 stages or strokes to create power. Fuel and air is sucked in, pressure is applied, an explosion pushes the piston down, generating power, and finally, exhaust is blown out. Only 1 in 4 strokes creates power. A two-stroke engine cuts the number of stages in half. As air and fuel are compressed and combusted simultaneously, more of the mixture is drawn into the system. On the return stroke, the exhaust is released and the process starts again. Power is generated every other stroke, twice the power.
So these cylinders are longer bore cylinders, which means that the piston travels farther up and down in the cylinder. It produces a lower speed but higher torque, which is perfect for freight applications. Let's take a look at some of these cylinders. We can see just they're enormous. This is amazing. I mean, this is almost a 70-year-old engine. It's in beautiful shape and still operational. Wow.
This 1,500 horsepower, 800 revs per minute freight hauling diesel locomotive could be found on virtually all of the major railroads at the time.
It's going to be really cool. We're going to get to see it running today.
Locomotive engineer Terry Wolf is on hand.
You want to open them about 2 turns.
Okay.
Perfect, right on. Okay, that's good.
First, the test valves are cleared and then the fuel pumps turned on.
Hit the bell, hit that start button, and hold on to it until she fires.
The two-stroke engine was powerful. But the turning point was in creating an engine that was also economical to run.
A steam engine only uses about 7 or 8% of the energy in its fuel to move the train forward, whereas a diesel is more like 40 or 50%. Because the EMD 567 was so reliable, so fuel efficient, and could be operated by so few people, it ended the age of steam in freight rail.
To see just how impressive this engine is, Agnes is taking a turn in the driver's seat.
This is amazing. I'm about to drive a 1,500 horsepower engine with 700 tons behind it.
Okay, now start bringing the throttle ahead. There you go.
This is the first time I've ever driven a train. It's way larger than things I normally drive. It's an amazing piece of engineering. It was something that really hadn't been done before. A two-stroke diesel that was reliable and had enough power to haul a lot of weight and do it over and over again, day in and day out.
This extraordinary two-stroke EMD 567 engine is part of a mechanical revolution that inspired the great cargo carriers of the future.
So this was kind of a proof of concept that this could work at a large scale, hauling large things, and really was the foundation for further development at bigger scales on land and sea.
Supertanker Europe, the largest oil tanker on the planet. Chief Engineer Zlatan Hirov is in the engine room to inspect an engine of epic proportions.
This has been one of the biggest engines ever installed on board of the ship. This is 9-cylinder, 2-stroke, turbocharged diesel engine. Maximum power of 50,022 horsepower.
It's one fantastic piece of engineering. The 1,100-ton engine is capable of pushing this 550,000-ton ship through the water at speeds of up to 19 miles per hour. The engine is directly attached to a prop shaft that drives this 103-ton propeller.
To be engineer on board of that vessel is really exciting.
But it's not just the power that makes this engine unique, it's the design. Despite its huge size for the power needed, this one is compact. It's a much simpler construction inside, with fewer moving parts. And its high power-to-weight ratio makes it ideal to fit and carry on board a ship, despite already weighing as much as 700 family cars.
This is one of the most amazing engines I ever seen. This is one fantastic piece of engineering.
Supertanker Europe reinvented how the world's shipping lanes look today and changed the scale of what can be achieved when trading by sea. Being part of the team that operates such an awe-inspiring ship is a career-defining moment for its captain and crew.
When I started my career as a seaman, I was dreaming one day to become captain of a big ship, but never dared really in my mind that will become true.
On this vessel, engineers came with great solutions to handle this vessel on most safe way.
It really makes me proud to be captain of such an amazing vessel.
At 249 feet high and 223 feet wide, Supertanker Europe is the largest double-hulled vessel in the world, capable of holding 7 times its own weight in crude oil. With its supercharged diesel engine that turns a 103-ton propeller, its pair of anchors each weighing 24 tons, and its incredible 250-ton rudder, Supertanker Europe has changed the face of ocean-going trade forever.
Efficiency has driven us to make ships bigger and bigger and bigger, but now we're running into the limits of how big we can practically manufacture. So it's possible that we will never see ships bigger than this made.
By looking to the great pioneers of the past for inspiration, adapting their ideas, refining their designs, and overcoming monumental challenges.
It's a sophisticated ship, able to power through the worst weather in all the world's oceans while packed full of dangerous cargo. It's a triumph of nautical engineering.
Many challenges, they've been set up and later on completed by the engineers. Being on board of vessel is exciting and interesting every day.